Hello everyone, welcome back. In this session, we will learn how to compute the slope and deflection using conjugate beam method for a cantilever beam whose flexural rigidity of the beam is not uniform. First, let me read out the problem. Determine the slope and maximum deflection at free end of the cantilever beam having different flexural rigidity using conjugate beam method. This is the problem. Here, the portion AC contains 2I and portion CB contains I. And this beam is subjected to a 10 kilonewton at the free end and 30 kilonewton per medium, 30 kilonewton per meter as a UDL in the portion AC. So, we need to compute the deflection delta B and theta B at the free end. First, let us draw the bending moment diagram for this beam. This is the bending moment diagram. We need to divide the bending moment diagram into parts. First part contains the bending moment for the cantilever beam for the load 10 kilonewton and second parts contain bending moment for 30 kilonewton per meter. Now for this bending moment diagram, we will apply M by EI diagram. So wherever there is a 2I, bending moment is reduced and the M by EI diagram looks in this pattern. This is the conjugate beam. As per the transformation of conjugate beam theory, fixed end converts into a free end and free end converts into a fixed end. This conjugate beam here is loaded with M by EI diagram. Now, let us convert this M by EI diagram into three parts, two triangular parts and one rectangular part, and calculate the shear force. Since there are two bending moment diagrams, shear force I have divided into two parts, that is shear force VB is equal to VB1 plus VB2. VB1 is calculated for this bending moment diagram. It contains the areas, two triangles and one rectangle, and weights for this area calculated as W1. Base is 1. It works out to be 5 by EI kilonewton. W2 is also a triangle. Half into is 2 and 15 by EI. It turns out to be 10 by EI kilonewton. W3 is 2 into, it is a rectangle, 5 by EI. This value is 10 kilonewton. Therefore, VB1 works out to be W1 plus W2 plus W3. Total value is 25 by EI kilonewton. Calculate VB2 from this diagram. VB2 is equal to W4. So its value is 1 by 3 into 30 by, it turns out to be 20 by EI kilonewton. Therefore, shear it is VB. The summation of both VB1 and VB2 works out to be 45 by EI. As per the conjugate theorem, B is equal to force B. Therefore, the value is 45 by EI kilonewton. Now let us compute the deflection for the same. Here we will calculate the distances of CGs of the load acting on the areas from the fixed support. X1 is equal to 2/3 of 1. It is 0.67 meter. X2 is equal to, it is 2 meter. This is plus. So X4 is equal to 3/4 times of 2 plus 1. It is 2.5 meter. Therefore, bending moment at B is equal to W1 X1 plus W2 X plus W3 plus W4 X4. Substitute values of weight as well as the CG distances from the fixed support, we will get bending moment, that is 6.1 kilonewton meter by EI. We know that maximum bending moment will be equal to maximum deflection. Therefore, deflection at B is also equal to maximum bending moment, that is 96.65 by EI. Similarly, let us consider another problem. This is a cantilever beam having different flexural rigidity loaded with uniformly distributed load of 12 kilonewton per meter and also a point load of 24 kilonewton as shown in the figure. We need to compute the deflection delta B as well as theta B. First, let us draw the bending moment diagram. This is the bending moment diagram. Maximum bending moment at the fixed end is observed to be 150 kilonewton meter for UDL, that is 12 kilonewton per meter. It is a parabola, and maximum bending moment at the fixed end, it is working out to be a 48 kilonewton meter for the load 24 kilonewton. For this bending moment diagram, we will try to draw M by EI diagram. This is the M by EI diagram. This is the conjugate beam. As per the rule, fixed end becomes free end and free end becomes fixed end. Now, let us compute the slope considering shear force. This M by EI diagrams are divided into 4 different areas, and load actings are W1, W2, W3 and W4. Here also have taken shear force for both the diagrams. Therefore, shear force VB is equal to 1 VB1 and shear force of diagram 2 VB2. VB1 is equal to W1 plus W2 W3. W1 is calculated as 1 by 3. Its distance is 3 meter and its height is 54 by EI. It turns out to be 54 divided by EI kilonewton. Similarly, W2 is a rectangle. Its base is 2 meter and its height is 27 by EI. It works out to be 54 by EI kilonewton. W3 is a parabola. Again, its area is 1 by 3 times. Its base is 2 meter and its height is by EI. It turns out to be 32 by EI kilonewton. W1 works out to be W1 plus W2 plus W3. It is kilonewton. Now let us calculate VB2. VB2 is equal to W2. Its value is 1 by 2 into 2 into 24 by EI. It is 24 by EI kilonewton. Therefore, VB is 160 kilonewton. As we know that slope at B is equal to shear force at B. Therefore, slope at B is equal to 164 kilonewton. Now, let us compute the deflection. Deflection, we need to calculate the bending moment. Bending moment at B is equal to W1 into 1 plus into X2 plus W3 into X3 plus W4 into X4. W1 we already calculated. Now we will calculate the X1 value. X1 is 4 times of 3. X2 is 2 by 2 times of 2 by 2 plus 3. 5 meter. It is 4 meter. And X3 is 3 plus 3 by 4 times of 2. It is 4.5 meter. And X4 is 2 by 2 plus 3 meter. It is 4.33 meter. Substituting the values of W and X, the bending moment, it is 585 by EI kilonewton meter. 5 kilonewton meter. This completes the problem.